The major problem for flash ADC, I mean especially for INL, is too many resistors to be matched in the upstream. So what we can help is interpolation. You can see, for example, here, this is the main voltage division for MSB bits. Okay, and how about LSB? Yeah, for example, for two LSBs, we have four quantization, four resistors to generate four quantization levels. Okay, in this way, you can see the complexity of the mainstream can be reduced. Yeah, how can I say? It depends on how much you would like to have for LSB. Okay, you need to pay attention to that. If you go back to see the real layout, how many resistors you need to have to cancel up to the second order? But why up to the second order? First of all, I told you already, for more than two devices, here now there is only one paper, can help us cancel to the second order mismatch for more than two devices. Okay, and for ADC, I think the number of devices is much more than two. Okay, but anyway, let's check this. How right now? How many resistors here? Okay, yeah, 0 to 3 for 2 bits. Okay, so for n bits, you will see two to nth power, 2 to nth power, and then by 2, because the left and the right is exactly the same. So the total number of unit devices for such kind of n-bit upstream layout, actually the total number, wow, 2n plus 1 power. Wow, it's really amazing. Okay, how many you can guess for 8 bits? Gosh, it's more than 60,000 something. Okay, even more than that. So it's ridiculous, to be honest. But if you don't do such kind of good enough layout pattern, the INL will be really terrible. So how to compromise that? Yeah, this is a very good way, very efficient way. You can see, but right now, because for the overall devices, for example, you have 2 LCD bits for interpolation. It means -2, right? So the overall number of devices here will be reduced by 4, right? Okay. Oh, sorry, 2 to 4 power 16. Sorry for that. Wow, it helps. It helps us a lot, because for the same 8 bits, right? Yeah, I told you already. It is 50 something or some. Yeah. Anyway, totally, the number is 2 to 17th power. But right now we reduced it by 2 bits. So overall, 2 to, right? I think this one is much easier to handle. Much easier to handle. Yeah, the total number right now is only 8,000 something. Okay, it's reasonable, because the layout pattern is quite regular. Okay, and to help yourself, yeah, the layout of such kind of unit device should be something like look like this. Okay, so if you put such kind of resistors side by side, this and that, well, can help you to connect all of them automatically. So you do, especially through the help of Laker. You can tell Laker how many devices to the row, to the column, then the instance, I mean the unit device. Yeah, you get the instance, then Laker will help you to automatically place all of them. After placement, according to the help of this wire and that wire, they will be connected automatically. If you do a good design, yeah, to the extra portion there. So from the beginning, you have the the left help. Then you copy all of them, flip it horizontally, put to the right. Bingo, you make it. And then you need to have the horizontal lines and the vertical lines to connect all of them, blah, blah, blah. I think it will become piece of cake. Okay? Anyway, interpolation can help you reduce the layout complexity very, very much. And the operation principle actually is still easy to understand. Again, this is for MSB. Yeah. And how to interpolate the other two LCB bits? We need 4 resistors to generate all the reference voltage for your comparator. Got it? That's it. But something will go wrong with such kind of too simple structure. Why? Yeah, in theory it is good, but in practice, if you consider the parasitic capacitance, resistance, it will also go wrong. Why? Because here, if you look back, you will see 2R in series. 2R here, 2R there, right? Because if the op-amp driving capability is good enough, we can pretend it is AC grounded, because if you look into the output of the op-amps with very good driving capability, we always think the output resistance is close to 0. Okay? Okay? So effectively, if you look back at the midpoint, you have 2R and the other 2R connected in series. So overall, you get 1R for your output resistance if you look back. Okay? Yeah, but the problem is, if you look at here, oh, sorry for that, 4R in parallel with the RO, but RO is really close to 0, so you get 0. It means what? The signal propagation according to time constant, okay? You get R here, you get 0 there, so the propagation time here is much faster than in the middle. I told you, that is a so-called clock skew. It will cause you a lot of trouble, all right? So how to balance the output resistance for such kind of interpolation structure? Yeah, you need to pay very, very much attention. Yeah, anyway, yeah, forget about this. And how? Okay, let's finish it. Here, delay time equalization. Okay? You can see, again, in the middle, how much is that? 1R, right? Because 2R in parallel with the other 2R, you get 1R. And this is the reason why, from here, you get 1R. Got it? Because this node is equivalently AC grounded. I told you already, to simplify the analysis. And there's a hey. I have 1R, you have 1R in the middle, you also have 1R. And how about here? 1R in parallel with 3R, right? After calculation, congratulations, you get this. Bingo. That's it. Again, this is a very good example for you. The so-called every detail. If you don't pay attention to this, sorry, even you get such kind of brilliant idea, the result is still failed after fabrication. Okay? So, to design a high-end, high-performance ADC is some kind of hardship. It's really, really hard, even for experienced engineers. So how can you equip yourself, prepare yourself well for your future? Yeah, you need to learn all those fundamental ideas. Okay. Unlucky, how can I say, sadly enough, from the industry, some of the managers told me after for their recruitment, I mean new graduates from the universities, many of them even from the top universities, I mean NTU, NCTU, Tsinghua, Chen. Many of the students even focusing on NRIC design, they still don't have good enough background. Yeah, I mean, yeah, for such kind of good enough understanding. So the fundamental requirement for IC design houses right now, they hope the university, the professors can teach all the background knowledges to help the students get well prepared. And how about the details? They told me, oh, we can train them in our own company, on-site training. Okay, yeah. Right now, they don't expect, oh, they can recruit some students even after they get the PhD diplomas, then they can be good enough to design ADC, to design PL. No. Forget about it. They hope all those students, even with PhD diplomas, will fully understand the operation principle. Okay, good enough. And for the details, they will coach them, they will teach them. It's really upset. But it is also a good opportunity for all of you. Okay, even TSMC, I cannot say MediaTek, but one of my students go to NTUST directly after graduation. In the past, it is not allowed. Okay, they only recruit students. They focus on students purely from top 4. Again, National Taiwan University, Chen, Jiao Tong, and Tsinghua University. I mean pure. What does it mean? From bachelor degree. Okay. If you graduated from here, then study a master or PhD programs in those top 4 universities, forget about it. You cannot get the offer because they have some kind of a fundamental screening system. If you submit your CV, your application form, you check, oh, your bachelor is not from top 4. Forget about it. Okay? Yeah. So, but right now the situation is changing a lot. Even TSMC in the past, our students were not allowed after graduation directly to their R&D center in Hsinchu. But right now, yeah, in that semester they send the team to visit me and told me and told our administrators here, our students are more than welcome to join them. Yeah, even after graduation directly to their R&D headquarters, blah, blah, because they get a lot of competition from China. Okay, so that is the good news for everybody in the class. And the other, maybe I told you already, the other major problem is most of the talented students from the top universities, they either go to study AI or they go abroad. They go to America, they go to Western countries for their master or PhD and never come back. This is the big problem. All right. Anyway, yeah, just do your very best. First of all, get good enough understanding. Okay. Don't be afraid. Oh, I'm not familiar with such kind of details. No worries. They will teach you when you join the company. No worries. Okay, but just do your very best on campus. You can see, first of all, the input will see much less capacitance, right? Because right now, 2 bits, I mean just structure, 2 bits for interpolation. And it means the total number will be reduced at least by 4 for the input resistance. And you will speed up the overall operation. Okay? Yeah, lower input capacitance, then you can say, hey, for such kind of, I told you already, to get good enough, high enough operation speed. The more capacitance means the more driving capability from your input, right? It needs a lot of power, but right now it is reduced substantially, so you can guess you can reduce substantially the driving power, but you need to pay power for those op-amps. Okay, overall the power will be slightly reduced. Okay, that is for practical implementation. Oh, it's really important because right now the overall circuit, the complexity, especially for your layout, I'm not talking about the structure. No, the structure is a little bit more complicated. But for implementation, especially for layout, the complexity will be reduced substantially, as I mentioned, even only 2 bits for interpolation. The layout complexity for your main art string will be reduced by 16 times. Bingo. That is really, really effective. Okay? And it will help you to enhance the, how can I say, the linearity. Especially if you look at here. See? Anybody have any idea? What is the advantage? What is the one of the major advantages of, first of all, I told you already to balance the parasitic resistance, right? But not only that, there is another quite important advantages with such kind of resistance balancing, right? Anybody? I told you already moments ago before the break. What benefit you can get? Averaging. See? Averaging. Anyway, but nothing is perfect. I need to pay attention to this. This is some of the quite practical situation for voltage division, because I told you already, wow, only 2 bits here, we can reduce 16 times in complexity. I mean for mainstream layout, right? Why we go for 3 bit? Wow, 3 means, it means what? Right? Oh, 64 times reduction in layout complexity. Why not? The major issue is this. Again, this is the major concern for interpolation. What you can see is, for your real simulation, you can see in the middle, no problem at all. What will be the problem? 1/4 and 3/4. They are not ideal. Okay? From your eyes, you can see it is not perfect for voltage division for such kind of interpolation. See? And this is the reason why usually for such kind of interpolation, only 2 bits. Because more than that, it's really hard to get very good from 0, 1.8, right? 1/8, 2/8, all the way. No, it's really hard to achieve. Some of my students did such kind of design in the past, and then they gave up. I mean, for more than 2 bits. That's too hard to do accurate enough interpolation. So lesson 1, 2 bits, good enough. 1 bit is perfect. Okay, 1 bit. Yeah, as you can see from the plot here, perfect in the middle. But 1 bit for interpolation, actually, I think that is too expensive. Too expensive. Yeah, because you need to pay a lot of chip area and power for the op-amps here. Too much. Okay, it doesn't deserve. So, I guess the best situation is 2 bits. Not less, no less, no more. Okay, not more, not less. 2 bits for interpolation, good enough. And please try your very best to fine-tune the interpolation result. Okay, that is what I recommend you. Okay, anyway, yeah, for the others, you just have a read by yourself, not too much. And what is the accuracy? Yeah, how much the gain is required for the op-amp? Usually around 10 or something. Okay, not too much for 100 or 1000. It will waste too much power of you. This is some kind of value from our experience. Okay, for all those good designers, at least the recommendation is around 10. Yeah. Anyway, anyhow. Okay. Yeah. Daytime equalization I told you already. Yeah. Next. A very, very important, very high speed ADC design. We call it time interleaved ADC. Yeah. For engineers, I cannot say you use such kind of ADC almost every day, but for your measurement, you need it almost every time. Okay. Yeah, that is the main idea behind your digital oscilloscope. How can you achieve? More than 10 or 15 years ago, I bought a very luxury oscilloscope, digital oscilloscope, maybe from Tech or from Angeland. Right? And nowadays it changed its name to be Keysight or something. From HP to Angeland to Keysight and to what? I have no idea. Okay, but Tektronix usually has the same name. Okay, yeah. More than I guess 10 or 15 years ago, I bought one. It's really expensive, quite many million NT dollars each. Okay, in that era, the real-time sampling rate is already, to my memory, 40 or 20. I forgot, but anyway, 40 or 20 gigahertz. And for you to have a good enough waveform display on the screen, we need 8-bit. Okay, that is the common spec. 8-bit, I think, is the common spec. But how to achieve not a gigahertz operation? No, we are talking about tens of gigahertz. Right now, maybe 80 gigahertz or even 100 gigahertz for the top, the most expensive digital oscilloscope. How to achieve it for one single ADC? I promise you, no way. Okay, never mind how good the process evolution is. I still told you, no way. All right, for a single ADC above gigahertz, I think maybe only 3 to 4 bits. Yeah, if you would like to achieve 80 bits more than 1 gigahertz, you had a better run for your life. No way. Okay, but it is contradictory to the operation of our digital oscilloscope, because right now the real-time sampling is more than 80, at least 80 gigahertz. Why? And how to make it? Yeah, a very important idea is time interleaving. Okay, this is the overall structure for you. For example, for look, 8-bit. That is the key common spec for digital oscilloscope. Never mind how fast, how slow they operate. They still have the same thing. Not more than that, not less than that. 8-bit, a common spec. But the key difference is here, 20 gigahertz, for example. How to make it? Oh, all right. You can see they have totally on the same chip 40 8-bit ADC operate at 0.5 gigahertz. Totally they have 40, right? 40 by 0.5. They make 20 gigahertz. That's it. No secret. Okay? But all those ADCs operate sequentially. Not in parallel, no. Sequentially means what? Yeah, from the very beginning. The first, okay. Yeah, to help you. All right, okay. The first, and then the second. I mean, according to time scale, right? The first, the second, the third, all the way to the final. And then the first, the second. So for each one, you have 40 clocks for your operation. We can lower down the operation speed for each one very, very much. So if you look at the overall structure, we have a very high speed, the highest speed for that kind of sample and hold. Okay, I hold it, then for each one, you hold yourself for conversion for 40 cycles. Piece of cake, even for 20 years ago. Okay, and then the second, the third, all the way, yeah, to the last, and then again and again, do such kind of rotation. Okay, yeah. So we call it time interleaving. 0, 1, 2, all the way to 39, 0, 1, 2. That is the so-called, in time domain, we call it time interleaving. Okay, that's it. No, piece of cake. Everybody can make it. No. The hardest part right now for design, first of all, how to design such kind of very good, with enough accuracy, operate at such kind of the highest operation frequency according to your real-time sampling rate. See? Usually, the design for such kind of very high frequency sample and hold circuit is even harder than each ADC. Okay? Sometimes we don't use the same process. For example, silicon, germanium, blah, blah, very special process for this. And for that, for all the common ADCs, CMOS will be good enough to reduce the power, the cost. Okay? So the bottleneck, first of all, is this. Secondly, that. Why? You can see for each cycle, you need to get one output from one ADC. First of all, this, the first, the second, all the way to the bottom. So what is the operation frequency? Again, the same. Right? If you look at your mobile phone, or you look at, have a look at the CPU for your desktop, how much they can operate? Here now. The maximum, I guess, 3 to 4 gigahertz. But see, 20 gigahertz. Even for DRAM, or SRAM, maybe SRAM, not DRAM. DRAM is too slow. That is very important. Cache memory. Okay? Cache means what? Very high speed SRAM. DRAM, not good enough. Okay, but 20 gigahertz, I promise you, really hard to design. Right now, it's already more than 80 or even 100. That is also very hard to implement, even for digital circuit designer. No, it's not a piece of cake. No, never. Okay, so again, the major problem right now is not for ADC. No, piece of cake for ADC, but this and that will become the most important bottlenecks. Okay? So it will be really expensive for this, not only this, but also that. Very, very expensive. The key problem is, I got some experience because during my negotiation with electronics salesman, they told me, "Oh, professor, right now you don't have enough money right? No worries. You can buy the same model, but because for the model name, maybe DSO, blah, 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 dash something, right? With different sequence number here, even for the main one, are the same, but with different subscript or something, yeah, you can get cheaper, much cheaper price. What is the major difference? If the main sequence number is the same, then they can operate at the same frequency. Okay, but for this one, it means what? Here. So this, yeah, related to how fast the sample and the whole circuit can run, okay, can operate, and then related to this one, cache, how much cache you can have. Okay, wow. For the first moment, it sounded reasonable, but after thinking, I figure out, oh, ridiculous, because for such kind of very high-speed operation memory, you don't have, just like your motherboard, just like DRAM, right? You have some kind of slot to plug in your DRAM. If you offer me more money, I plug more DRAMs for you. That is the usual case, right? But it doesn't work for such kind of very high operation. No, no way. All those, not only the ADCs, but also all the cache needs to be on the same chip. So for the current moment, I don't have enough money, so I buy the same model, but with different sequence number here. I pay much lower price. For next year or 2 years later, I get money from the other project, then I can upgrade. But how? How can I install more memory on chip? No way, right? So what does it mean? They have the same memory on chip. If you pay me less, I have some kind of program to run the setting to limit. Oh, you can only use 1/10, 1/100 of the memory. That's it. But they have everything on the chip, from the cheapest model to the most expensive model. They have the same hardware. The only difference is software setting. Okay, so yeah, you learn another lesson here. That is so-called channel depth. For each channel, how many samples you can get continuously. Because after the cache is full, you need to move the content from cache to DRAM or something on your motherboard. Okay, that is another story, but you need to wait. So you can have, oh, continuously maybe 4K and then move out. Oh, to move them out, you need to wait for a much longer time. Then resample your input. Okay? So how much is the memory depth for each channel? I promise you, for the same model name, you get the same hardware. Okay? If you pay less, then you can only use very little of them. Pay more, then they change the setting to 100% of the cache you can use. I mean, you pay the most money, you get all of them. It is ridiculous. So after I figure out, they say, okay, yeah, you offer me a little bit more, then I can help you, yeah, to get 100% of the utilization. Okay, that is a very good story for me. So I pay a little bit more than the lowest price. That's it. But I get the maximum utilization. I don't need to pay 100% of the money, but I can utilize all of them. Okay, 100% of the cash. I'm really happy because I'm a smart guy. Even I didn't know how to design such kind of time interleaved ADC, but I got the important idea, how they operate the oscilloscope. Then I get a sweetest offer. They want me, don't tell the other guys, especially across the street to NTU professors. Yeah, because they have enough money. They pay 100% of the money for the same model. Yeah, so this is the operation I told you already. For the first, for the second, for the third, all the way to the final one. That is the so-called time interleaving. Yeah, input, sample, and hold is the most critical. Is the most critical part. Yeah. So usually, or sometimes, realized in different. I told you already, such as gallium arsenide, blah blah. It is much. I cannot say much faster. It is faster than CMOS, but it is much more power consuming and much more expensive. So they wouldn't like to use gallium arsenide for all the chips. It will become too expensive. Again, only for the input, sample, and hold. For all the others, hopefully with CMOS. Okay? Yeah. The other issue you need to know. Yeah. What is the second challenge? This is the first challenge. The second challenge. Oh, sorry. The third challenge is you need to match all those ADCs in theory. Why? Oscilloscope is supposed to measure shear DC. I mean, the input can be DC, right? If you have DC input, then hopefully on the screen you will see a flat line for your DC input. The higher in V in, well, you get higher linear line, horizontal line. But if they are not matched, what do I mean? With the same input, they get different output. Oh, it's really troublesome, right? Right? Because for the same input, you will get some different output, some periodically. Because again, from 0, 1 all the way to 39, 0, 1 all the way to 39. So, what is the period for such kind of output, even you have DC input? Yeah, that is okay, that's it. Periodically, you will get some signal like this if they are not matched. Not only for DC input, but also for your AC input. You will have such kind of, according to superposition principle, okay? Yeah, you will get your AC input plus such kind of periodical signal. So, for your spectrum, oh, sorry. If you look at your spectrum, usually we only focus on positive spectrum, okay? For example, you have a sine signal for input. You have one term here, right? Okay? That is for your input. But you say, hey, look. Okay? Yeah. The second largest actually is your sampling frequency divided by the total number. This one, if that is M, okay? That is the real sampling rate, the highest sampling rate divided by the number of ADC interleaved. All right? Not only your real input, you will get this, and it's 2 times, 3 times many high order harmonics. It will hurt, for example, your ENAB, your signal to noise ratio, because it will become some kind of noise for your measurement. Okay? It's really, really harmful. So please match all those. For M channels, right? That is what I explained to you. You will get some kind of interference, especially not only for your DC, but also for your AC. But how to match them? I guess calibration. You need to calibrate all of them one by one to get the same output, hopefully, after fabrication. Okay? So that is another trouble. How to match 40 or 80 of them? Wow. It's really, really troublesome. Okay? Yeah. That's it. That is the top secret for high-end oscilloscope, digital oscilloscope. Okay, let's go for the other one. Half flash. Or we call it sub-ranging or two-step flash ADC. Yeah. For example, if you have 80 bits, then the complexity will become 2 to H power. That's too much. So for two-step converter or half flash, we have 4 plus 4. I mean in theory, in practice, no. 4 MSB, and then 4 LSB. Okay, half flash for LSB. That's it. Half flash for MSB, half flash for LSB. Okay, so what is the concept is we do exactly the same conversion for half flash or full flash. I don't care. Okay, the operation principle for such kind of flash conversion is exactly the same. The only difference is after conversion, we convert it back through the help of DAC to get the difference from your input. So you can see, after sample and hold, we do exactly the same flash conversion to get the digital output for your MSB. And then through the help, if the DAC is ideal, but in practice, again, usually 2 bits higher in accuracy. Okay, for this one. Okay, anyway, yeah. For what? We convert back the digital to analog, then see the difference. So for MSB, for example, 1, 2, 3, 4. Yeah, 2 bits here, 2 bits there. Okay, yeah. So for example, you are here. All right, you might say, 0, 0, 0, 1. Congratulations, you got 0, 1 here, right? 0, 1 only for digital. That is the digital representation. We need to convert it back to analog. 0, 1 means this one, this quantization level. Then the real input here, right? The sampled and hold input will be sent here and subtract from the DAC. The DAC help you to generate this one. So you get the difference, right? And then enlarge it by 4. Why? Because 2 bits. Enlarge it by 4 means the maximum one, very close to this one, right? But it is only for the quantization level, it is only 1 divided by 4 of the full range. Okay, so we need to multiply by 4 to expand, to enlarge the error. I cannot say the error. Usually we call it a very specific term. We call it the residue. Hopefully the spelling is correct. The rest. Because again, we have such kind of quantization, right? You are here. Then the difference between your real input value and the representative quantization level, the difference, we call it residue, need to be expanded. And then converted by the LSB bit. That's it. They do the same thing, like this, in theory. Okay, that's it. If you have, for example, 8 bits, 4 bits here, 4 bits there, so how much you need to enlarge it to amplify it? 2 to 4 bits, 6 times. That's it. Okay, again, the idea is to make the residue, I mean the difference between your real input and the DAC output, to enlarge it to fully cover the reference range. Okay, and then digitized by the LSB flash ADC. That's it. Okay, and after conversion, congratulations. Yeah, you can combine the MSB bit and the LSB bit to be the real output. So we call it digital assembler. But that is only in theory. In practice, everything is not perfect. So even for the DAC, yeah, for the gain, they, for example, 4 plus 4, yeah, the gain needs to be exactly 16. Forget about it. No, after fabrication, it will become larger or smaller. If you did everything you can, then 50% of the gain will be larger than 16. 50% will be smaller. Okay? For larger one, you will have overrange error, blah, 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 blah. So anyway, anyhow, you need to do correction. Okay? You not simply, oh, MSB here, LSB there, oh, combine them for upper. No, 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 no. You need to correct. That's it. Okay. So usually we don't have 4 plus 4. No. Usually 4 plus 4.1, 4.5, or even 5 to get better accuracy. But how can you combine both of them? Not only assembler, but also assembler 组合，把它拼在一起。Also digital correction. Okay, that's it. So that is the idea for half flash. The major purpose is to reduce the implementation complexity. Wow, from 8-bit all the way, you can see you reduce the complexity by 16 times. For layout, you reduce the complexity by bingo. Fantastic. Okay, but nothing is free. You need to pay for what? The conversion speed, in theory, will be reduced by 2. Okay, because from the beginning to the end, you need to pay more time for delay. Okay, that's it. All right. And this structure is more popular because you can reduce, substantially reduce, 大幅减少 the chip area and the power. All right, and also some of the demerit, yeah, because I told you from the input to the output, you need to face more delay. It means the latency, I told you already, right? The latency will be increased, right? But these demerit, disadvantages will be a little bit reset or compensated for what? Because right now you have only 4 bits here, 4 bits there. So from the input resistance, okay, yeah, the input, sorry, capacitance will be substantially reduced. So in theory, you can speed up the operation, right? So they can help each other, even though you get larger latency, as I told you. But much less input capacitance will help, yeah, to neutralize the impact of such kind of larger latency. Okay, so in practice, the speed won't be slowed down too much, only a little bit, only a little. Okay, that's it. And this is a very good example for you. From the beginning, you need to do sample and hold, so you need 4-bit ADC, but the accuracy needs to be 8-bit. What do I mean? 4-bit ADC with 8-bit accuracy. I explained already, according to INL, if it is half LSB, then 4 bits means you get the effective number of bits is 4. If you reduce the error to 1/4, then you got 5 bits in accuracy, right? Right? That's it. So how to make it how to make the actual accuracy for 4-bit ADC to achieve 8-bit accuracy. It means what? The LSB, the error needs to be reduced by 16 times. So the design for this one should be much better than the other one. Okay? Then the other ADC, sorry, the other ADC here. So the MSB ADC, the design is much harder than the LSB ADC. Okay? Don't simply duplicate. Oh, I have do a good enough job for this one, then copy and paste to the others. No, 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 no. If here is good enough, it means what? Over design for that. Okay? If you do a good job for this and copy and paste to MSB, sorry for that, the accuracy is too less. Okay? So please pay attention to this. For all those two ADCs, they need to be designed separately. You need to pay much more area, much more attention for this one, and then you can reduce the area of the power consumption for the LSB ADC. Got it? They cannot be exactly the same for real design. Anyway, for 4+4, you can see, hey, 4 MSB here, and totally only 8-bit. Why? I have 5-bit LSB. Simply because we need to make the final error less than half LSB. So 1 extra bit for your LSB ADC will help you to achieve this target, this goal for your own design. Got it? That's it. Okay. So if you have a detailed look at the specification, 8-bit. Sorry, for my previous one, I write only 4. That is incorrect. I'm not the one to write it. I got the slide from the others. But this night I checked. Oh, that is really embarrassing. 8-bit inaccuracy for your MSB ADC, MSB DAC. Okay. And then how about your final one? Yeah, you only need 5-bit inaccuracy. Okay, and then do the so-called error correction. All right, distort correction, blah blah blah. Yeah, and we can duplicate the same idea. Why? If you would like to reduce the complexity, again, we can have 3-step flash. The same thing, right? For example, if you have 9 bits, then we can have 3 plus 3 plus 3. You do the same thing, the same logic thinking. That's it. Yeah, you can have more than 2, more than 3, more than 4 steps. To the final, for 8-bit flash, you can have 8-step flash. Right? 8 steps. And it means what? For each stage, the minimum is to cover only 1 bit. Wow, piece of cake, right? Above it or below it. The full range. You only need to pay attention to the middle. Above it, 1. Below it, 0. Oh, piece of cake, right? That's it. Okay? And then we can go further. The other, but right now, the problem is the more steps in theory from the input to the final output, the more latency. All right? And the conversion speed will become slower. I mean, only in theory. The throughput. Okay? 产出 throughput. Anyway. So, how to enhance your throughput? We can go for pipeline. But what is the difference, the major difference between pipeline ADC and multiple step flash ADC? The only difference is this: sample and hold in between stages. If you look at the original structure, we have only sample and hold to the input, and then nothing inside. So after I convert MSB, then get the residue the difference between your input and the deck output, amplify it for the next stage, and again get the residue, amplify for the blah, blah, blah. So you need to wait for the input propagate to the end and then get the final output. So the latency, the more steps, you get more latency, and the throughput will become less than before. The more steps means the less throughput. But this is a very good innovation. Sorry, I need to make it become red. Okay? Compare 3-step flash ADC and 3-stage pipeline ADC. In theory, what is the difference? Sample and hold, sample and hold between adjacent stages. That's it. 好 ，Pipeline ADC 跟 Flash ADC 最主要的差别就是在2级当中，连续的2级当中，你要不要插入 Sample and hold， 就这样子而已。没有插入就是 Flash， 有插入就变成 Pipeline。That's it. Okay, but you may be curious. Hey, I need to pay money. I need to pay chip area, power consumption for sample and hold, right? Sample and hold is not free. You need to pay for it. What benefit I can get with such kind of sample and hold? You can see for the first input, after I sample and hold, I do all the conversion, I get the residue, I amplify it, then sample and hold for the next stage. But after sample and hold, I have nothing to do, right? I finish all my job, sample and hold the final result for the next stage. Hey, what I can do? Oh, I can get the new sample to process. It's MSB bits. Got it? That is the logic thinking for pipeline. So again, if you have 9 bits, you have 3 bits in theory. Okay, but that is MSB and that is LSB, right? So in time domain, from the beginning, you get the first sample. Okay. Then after I finish my job, then for next cycle, the first okay, sorry for that. ABC will be easier. Okay, A input with 3 MSB. Okay, and then maybe 4 plus 4, 2 stage, easier to understand. Yeah, 4 MSB, right? So for the next cycle, because I already hold the final result, so for next cycle, will be processed by next stage. How about myself? I'm free right now, so I can process B next input for MSB. Okay, so you will see something very similar to pipeline deck. Yeah, for A for MSB, right? And then A for LSB. But I can process B for MSB and then B for LSB at the same time C for MSB. Blah 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 blah. Okay, it means what? After some cycles, you will get 1 output per cycle. The throughput will be enhanced substantially. That's it. That is the benefit for pipeline operation. The throughput will become 1 output per cycle. Got it? For 3-step flash, you need to get 3 cycles per output. Per 3 cycles, you get 1 output. But right now, we make it 1 output, 1 cycle. Okay? You can speed up the overall throughput. No, not speed up. You can enhance the throughput very much. And this is the reason why pipeline ADC actually is much more popular than pure flash. All right? Because the throughput can be enhanced very, very much. Okay, for detail, yeah. See? And then, if we look at the detail, in theory, they have the same structure from the beginning. The first stage, the second stage, all the way to the final stage. Okay? You have what? You have, for each stage, you have flash ADC. After conversion, you need the DAC to convert it back the original analog quantization level. Then take the difference, I mean the residue, and amplify to full range, and then sample and hold for next stage. Okay, and again, this is the major difference between pipeline ADC and multi-step flash ADC. That's it. Okay. To make the structure even more beautiful, even easier to implement, usually we combine all those into one switched capacitor circuit. And I explained the idea already to take up, let me think, to the beginning of the ADC. I told you, somebody say, hey, look, I have some kind of capacity array for my ADC, but I eliminate DAC, right? The same idea can be applied here. I told you already, it combines such kind of switch capacitor array. Actually, it combines the DAC, the subtraction, yeah, and amplification. Then hold the result. Okay, got it. So the other lesson here, you can see the same or similar important concept is applied again and again, not only for such kind of cyclic ADC or okay, I forgot. Okay, anyway, somebody claim their ADC doesn't need DAC, but in practice, actually, it only combines all of them. And the same idea can be applied here. Not only here, but for the other ADC design in the future for all of you. Okay? And this is what I'm talking about. You need to know all those fundamentally and most important ideas for all those circuits. Okay? And then in the future, you can apply again and again. That is what the industry hope our teachers can do to our students. Okay? So, yeah, for pipeline ADC, sample and hold, and stage 1, stage 2. For each stage, I explained already ADC, DAC, the difference, amplification, and then sample and hold for the next. That's it. And for each stage, you need to amplify the residue again to full range from 0 to V reference. Okay, so how much gain depends on how much bit you would like to have for each stage. Okay, for K bit in each stage, then AK means the gain needs to be this. I explained already. To make the residue, yeah, to be full range again for your next stage. All right. Okay, yeah. Switch the capacitor is very important for that kind of idea. Okay? Anyway, allow me to explain again how to do, for example, 2 times amplification and do such kind of voltage division. All right? Yeah, anyway. First of all, we need to charge to reset everything from the beginning. Yeah, I close it and close it and to the ground, to the input. Yeah, and then we can connect, okay, as you like, in this way. If you forget this, so after reset, we charge all of them, right, with the same voltage. But for the next time, I squeeze out all the charges to the output, to the C2, connected C2 to the output, because all the charges is squeezed to C2. So how to squeeze it if it is also AC grounded? The DC voltage here and there are exactly the same. Okay, then we can push all the charges from C1 to C2. So C2 get double charges. Okay, if C1 equals C2 exactly from the input sampling, right? They get the same, exactly the same charges. And if I connect it to the ground, I mean AC ground, okay? Yeah, here and there are the same. Then all, because the terminal voltage for C1 are exactly the same, no charges. Q equals CV. No charge, because the left and the right now are exactly the same. No terminal voltage means no Q. Okay? No charges. Where will the charges go? Because I cut the page here, and it is almost open, right? And this is also open. And then all the charges needs to be pushed into C2. So C2 gets the double. Okay? The double charges, it means here. Again, if the charges is increased by 2, then the voltage will also be increased by 2. That is the idea for voltage amplification. Okay, so you can see what is the key idea to implement voltage gain for 2, for 4. We don't realize anything like 3 times amplification, 5. No. 2 to some power. Okay, so how to make it for 2 bit? 4 times. Piece of cake. You do the same thing, right? C1, C2 all the way to C4. Then squeeze, push all the other 3 capacitors charge into the final one. Then connect it to output configurations. You get 4 times for amplification. So the major challenge is during the layout, how to make C1 and C2 almost exactly the same. Okay, and for 4 times amplification, 4 capacitors need to be exactly the same after layout. Okay, so you need to do very complicated one. But with very complicated layout pattern, you get a lot of parasitics. Okay, yeah. So take all the details by yourself. That is some kind of hard work you need to face. That is the challenge. Okay. Finally, how to get the difference? Oh, same idea. Okay. Anyway, because during conversion, we need to compare for each bit. It is 1 or 0. 1 or 0. I feel like I don't care. Okay. Anyway, how to get the difference? Again, after sampling, then we cut all the charging path for your capacitor, and then connect the terminal to this or to that. That's it. I told you already, for example, from the beginning, you already put V in here, right? Okay, so if you connect to the output, here now, you get V something. Okay, then how about the other node? You will become VR minus V in. Something very similar to this. Okay, if you would like to get V in minus VR, okay, you need to connect to your reference voltage first, and then connect to your V in. The next, you can reverse the subtraction. Yeah. Anyway, finally, you get this result. VR equals this minus that according to our operation. Yeah, dk is 1 or 0 as you like. I don't care. All right? So the most important issue is here, 1 plus C1 over C2. To make, ideally, 2 for gain, you need to promise me. Okay? That is your own responsibility during the layout. You need to make it. And then we go for comparison. Okay? Again, to reduce the power consumption, especially for high-speed operation, we don't use static comparator. We use dynamic one. And allow me to show you the most important, the most commonly used dynamic comparators. From the beginning, you can see people use such kind of simple dynamic comparator. Actually, you can see they have such kind of switches. If you don't need it, we cut it. For example, if CK becomes 0, okay, for MOS off, and CK bar 1 off, right? For what? Power saving. That's it. Only when you need the comparison result, we turn on the switch, yeah, connect it to the ground, connect to VDD. Oh, it operates. After that, we shut it down for power saving. It is really important. Okay? But in this way, what is the major problem? After power on, no. After you shut it down, right? We to save power for some time, and then you need to reactivate it. 重新启动. You need to activate the whole circuit. So to turn it on and turn it on, right? But from 0 to 1, I mean from no power to to get some current from VDD all the way to the ground, you need to wait for a longer time. Okay, because some of the transistors are cut off. From cut off to saturation, sorry for that, yeah, or to be fully turned on, you need to wait. It will waste a lot of speed. Okay, you will waste a lot of time. So the next generation is pre-charge. Okay, so what does it mean? Look, if you don't need, again, you can cut it. Okay, but when I cut it, you can see CK bar help you to charge the node for V out to VDD. Okay, and then for real, but no worries. Hey, I charge the V out and V out bar to VDD. Will it consume some power? No, because here and there are cut off. Okay, so we only prejudge it to V out. And then for real operation, C clock needs to be 1, right? It will be shorted, and cut off. Right? Then for the output, I don't care the V in or V reference, who is larger than the other. I don't care. I need to tell you why we need to do such a prejudge, because NMOS runs 2.5 to 3 times faster than PMOS. And this is the reason why before comparison, we pull all those V out and V out bar to VDD. Okay? And according to V in larger than V reference or less than V reference, you need to pull down here or there to ground. Right? Right? But again, NMOS operates much faster than PMOS. In this way, we can speed up the whole operation. So we need such kind of pre-charge. Okay? And again, this is some kind of detail. Actually, if I don't have time, I will skip it. But I think that is really important for your future, for real implementation. So I spent some minute to to explain how it operates. The other problem is the so-called metastability, 假稳态. Again, if I'm larger than you, then V out need to be 1. So I need to pull down this node to 0, right? And on the contrary, if I'm less than you, then I need to pull down this node to ground. Anyhow. But the problem is, if V in, for example, if V in and V reference are exactly the same, right? Which node to be pulled down to ground? Nobody knows. They will be. Okay, so both V out and V out plus will be pulled down to some voltage, just like this. Higher or low, I don't care. Okay, it is neither 0 nor 1. It means after comparison, you also cut it off, right? And what is the V out for the next stage? Nobody knows, because the final voltage is neither 1 nor 0。各位这样听懂哈？如果两个输入电，这个跟那个完全一样，理论上他们两个 node 都会被往下拉，因为这两个都会partially conducted. Okay. So what is the final voltage? Nobody knows. It is not 0, not 1. Okay. So how about the next stage? It will be curious. What kind of input it has? It is not 0, it is not 1. So it depends on the mismatch or the threshold voltage. Okay? The threshold voltage for your next stage, maybe here, maybe there, it will cause a lot of problem. So we call it metastability. That's it. In practice, in theory, if they are exactly the same, it will cause you the problem. But in practice, if V in and V reference is too close to each other, then V out and V alpha will be pulled down partially. Okay? So anyhow, it will become some kind of problem for your next stage, because the next stage again will be curious what the real value for the input, because for them the input needs to be 0 or 1, but right now you provide something in between. Okay, so what is the result? Uncertainty. 不确定. So we call it metastable output. All right. And how to solve it? No. It is proved already. It is proved already. There is no way on earth to totally solve such kind of metastability. No, you need to face it. But again, the higher gain, the less probability for metastability. Because the higher gain means what? Yeah, for such kind of partially pull down, I can pull it all the way to 0 if my gain, if my driving capability is larger. Okay? Anyway, that is a very important idea for you. Okay, the final comment for metastability is it happens. Sometimes you have no way to reduce the probability to 0. It means what? Never mind. Only if there is some kind of comparator. I don't care. Dynamic, static, anyway. Never mind how good design you are, how good design you have. There is still some probability to get metastability. It means sometimes your ADC output will be totally incorrect. Okay? You need to face the consequence. Yeah. The better ADC, the smaller probability, but nobody can reduce it to 0. No way. Okay? You need to face the consequences. But how to solve it? I told you already. The more gain for your comparator, or the more driving capability for those, okay, you can reduce the probability for metastability, but not for 0. Okay, great. To get larger gain, to get more driving capability, it means more chip area or more power. Again, you need to do trade-off. What? That's it. Okay? Yeah. So this is some kind of standard pipeline ADC sample and hold in the input, each stage all the way to the final. Then you combine all of them. And again, you need to do digital correction. Yeah. And I am not the teacher to teach you how to do such kind of digital correction because I am an analog IC designer. If you are curious, Google online. Get help from IEEE Explorer. Okay. Anyway, even you only Google online, again, you can get the Verilog or VHDL code for this one. So you don't need to worry. Even though you don't understand, you can get help from the others. You only need to change how many bits per stage, blah, 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 and overall how many. They have some kind of parameters for you to change. Then you can do cell-based design to implement all the digital circuit for this. Okay, forget about it. All right. For such kind of structure, it is good for medium to high speed. Yeah, and also for medium to high resolution applications. So maybe more than 10 years ago, pipeline ADC is the best, not only for the industry, but also for the universities. But nowadays, more and more researchers actually, they turn their head away from pipeline to SAW. Okay. Yeah, I have no idea. Maybe according to better detailed circuit inside to speed up the operation of SAW. And also, SAW operation is much easier to understand than pipeline. Okay? So that is the reason why more and more engineers focus on SAW. But in theory, SAW operation is slower than pipeline. But again, we have new structure, we have new circuit, and we have new processes to compensate for the speed operation for SAW. Good enough. Okay? Anyway, so this is a pipeline ADC example from maybe from TI. All right? So overall, it has 6-pin output, but you can see 3 plus 3 plus 3 plus 3, then plus 4. Okay, and then combine all of them with digital error correction. Sorry, not from TI, from ST. Okay, 意法半导体. Right now, maybe. Okay, I have no idea whether ST is still alive or not. Maybe it's still alive. And this is for each stage it looks like this, and this is the layout for the overall chip. Okay. All right. Before I finish the class today, hopefully, yeah, because cyclic ADC, or we also call it a rhythmic ADC. Anyway, it is quite similar to pipeline, right? For pipeline, the first conversion, after first stage, we hold it for next stage, and hold it for the third stage, right? But if you reuse one stage, for the first conversion, I hold it, then I use the same stage, the same circuit to convert the next into the next. Then you make it from pipeline to cyclic. We reuse a single stage for all those, right? The major difference is for pipeline, after sample and hold, I do all the conversion and hold my result for next stage to process. And after the process of next stage, it holds for the third stage, blah, blah, blah. But right now, we reuse all the stages. We only have one stage, one hardware stage. So after the first stage conversion, I hold it for myself. So myself need to do the second conversion and hold it again for myself to do the third conversion all the way to the final, and then you get the output. That's it. In this way, we can reduce the overall chip size very much. You can reduce the cost very much. But again, nothing is free. You need to pay for worse error, much larger error, because I told you the error for this, for that, blah, blah, all of them will be exactly the same. So the error will be accumulated from the first stage to the final one because you use the same one for all. Okay, yeah, the same idea for cyclic deck or pipeline deck. All right, and that's it. We make it for from pipeline to cyclic ADC. All right, and I told you already. Oh, significant reduction in hardware, but more error and the throughput will be reduced. That's it. Because myself need to do it again from the beginning to the end. So you need to wait for me to finish all the stages for conversion, and then you get the final output. So the throughput will be, yeah, M means the stages, okay? It will be reduced. Per M stage, you get one output. That's it. Okay. All right. And this is the other view for cyclic ADC. Again, for example, only one bit in each stage. So for the first conversion for MSB, you need to, for example, this is your input, right? You need to compare the input to the reference in the middle. Larger than that, you get one. Okay, so you get one here, right? And then get the residue, I told you already, and multiplied by 2 because you have only one bit. Multiplied by 2 and compared to this one, oh, smaller than the reference. All right, so you get 0 here, right? And the residue is multiplied by 2 again for the final stage. Final comparison. Ah, larger than this one. Oh, congratulations. So the result is 101. That's it. Got it? Very easy to understand. All the conversion are done by the same stage, by the same hardware. That's it. That is for cyclic. Okay? Yeah. This is for your reference. Oh, okay. And how to do such kind of multiply by 2? The same idea I explained for quite many times. Okay, squeeze all the blah, blah, blah. Okay, yeah. Okay, I told you already. So, this is the end of today's class because I have a very important meeting. For next week, I would like to finish very soon for oversampling. Oversampling, you have many kind of structure, but we only focus on this. Okay, because that is the most popular, the most efficient way to do such kind of oversampling structure, oversampling ADC. After that, little comments for testing, then we go for the next part for ADC testing. But I hope I can finish all of them in next week and go for PL at least. Okay, I need to finish all the content for PL for you because this is already the second week for June, right? We have very few left. Yeah, when necessary, maybe I will help from TA to. I hope I can finish the most important content for PL. That is my duty. Okay, thank you all.